The title of this presentation is PA Circuit Level Validation of a New Nonlinear GaN Model Library. This work represents a collaboration between Modelithics and Qorvo. The purpose is to demonstrate the effectiveness of a new GaN model library for supporting PA designers, specifically those that desire a simulation-based design flow. The models provide advantages to designers who want quick turnaround designs but may not have measured load pull data at their target frequencies. The library currently represents 11 die and 20 package devices with at least 18 more models in the works. Currently version 1.6 library is now available on the Modelithics website. Some of the advantages of the model library support that is being provided by Modelithics and the features of the models are listed here. Just to name some of the features, for some models the quiescent bias voltage is scalable, so the models have ambient temperature and the models have self-heating effects included in the models. One of the important PA design trends that is being supported is to provide access to the intrinsic voltage and current nodes of the transistor. Some of the models where bond wires are used in the measurements have switches to turn on and off the bond wire effects. And there's a new model format that we'll be working on for future releases. One of the nice things about this model library is that it's provided free to designers. The model library supports currently Keysight ADS and NI AWR, electronic design automation software. Within each of those platforms, model information data sheets are available by clicking on the help buttons. Also, the models themselves are accessed by a request on the Modelithics website at the link shown here. This example just shows a model icon for a 6-watt GaN die. We're illustrating here some of the model inputs. In this particular case, there's a bond wire removal feature. The quiescent bias voltage is scalable, and there's a self-heating factor and temperature inputs here. So we can see temperature effects illustrated on the IV performance in the upper right plots, and in the lower plots here we can see the effect of the self-heating factor, which is adjustable, for example, according to the duty cycle of a pulse waveform. The intrinsic voltage and current sensing feature is illustrated in this slide, where we can see the intrinsic voltage and current waveform overlaid in the plot in the middle, and on the right we see the dynamic load line illustrated for external sensing of the voltage and current, where the parasitic effects are causing the apparent IV swing to go outside of the IV characteristic limits, whereas the intrinsic sensing shown in red is more limited to the actual IV plane. Just to illustrate some typical design methods, if one doesn't have a model, skilled power amplifier designer can start with a small signal conjugate match and use perhaps a load line method or what is known as Cripps technique to get an estimate of the load impedance to get maximum power out of the device, and then manually tune performance on the bench. This has been done for years, actually. Another approach is to use load pull data and a small signal match on the input and use load pull data to optimize the output matching networks. With a nonlinear model that is properly prepared with known reference planes and measurement validations, a more flexible design approach is possible, and load pull data can actually be generated at different frequencies, even though the model may be validated only at a limited number of frequencies with load pull data. Our recommended design approach would be to use accurate nonlinear GaN models. We believe such models should be documented well, so you know how well that model fits measured data and you have information about where reference planes are and things like this. Also, if you have passive models within your design, we recommend using models that take into account the board effects and parasitics properly, as is done in the Modelithics CLR library. Also, if your matching networks have distributed networks, that you need to use proper transmission line models or more appropriately electromagnetic models for your final design simulations. We'll go on now to present three examples. In the first example, PA design, this is a 5.8 gigahertz design. It was designed by Charles Suckling of Qorvo, fabricated and built by Modelithics, and compared to measured data. On the top right, we see power, PN, P out versus PN, gain, and efficiency. The measured data is the symbols and the model is the line. And on the bottom plots, we see the red curve is the model data and the blue curve is measured data. The second example, this one was built by Qorvo, by Kim Tran. We can see the model in the cases, the frequency sweep in terms of the gain and efficiency and output power, and on the right shows the return loss. In both cases, the simulation is in solid lines and the measured data is with symbols. In the third example, we see a design that was built as part of a student design project at the University of South Florida. And this design was a narrowband 2 gigahertz design. And we see that the output power, gain, efficiency is all very well predicted by the model. And also the frequency response was well predicted by the model. Recently, Matt Ozales from Keysight created a tutorial video illustrating a Class J PA design approach. The link to that video is shown here, and we see some examples of how Matt was able to demonstrate the use of the intrinsic voltage and current waveforms in a design flow. So in summary, we've demonstrated that successful first-pass simulation-based designs are possible using the new Qorvo GaN model library. Stay tuned for upcoming releases that will include not only more models, but also enhanced model features. The model's free to Qorvo-approved designers, and it can be requested at the link shown here. To get support for the models, contact Modelithics at support@modelithics.com. For product and application-specific support, the email for contacting Qorvo support is listed here. Thank you.